Imagine, for a moment, a place so distant, so profoundly alien, that it exists on the very fringes of our cosmic understanding. A world of perpetual twilight, cloaked in an atmosphere of frozen gases, where winds scream at supersonic speeds, a true giant shrouded in deep, chilling mystery. This is Neptune, the farthest known planet in our solar system, an enigmatic blue orb that for decades has remained largely a whispered secret, a blurry enigma at the edge of humanity's reach. Unlike its more flamboyant gas giant siblings, Jupiter and Saturn with their iconic storms and dazzling rings, Neptune's remote location has historically kept it veiled, limiting our ability to truly comprehend its wild, unpredictable behavior, its furious weather systems, and the profound forces that govern its colossal being. It was a distant, serene blue marble, or so we thought, until a silent, unseen drama unfolded billions of miles from Earth. The serenity, however, was a deception, a cosmic mirage maintained by sheer distance. That perception changed dramatically when the most powerful and sophisticated eye humanity has ever placed in space turned its gaze towards this distant sentinel. The James Webb Space Telescope, JWST, a marvel of infrared engineering launched with the primary mission of peering into the very first moments of the universe and dissecting the atmospheres of alien exoplanets, had a routine, almost mundane task scheduled. It was to conduct standard observations of Neptune's swirling cloud formations, its peculiar magnetic field behaviors, and the subtle atmospheric shifts that hint at its internal dynamics. No one, not even the sharpest minds at Mission Control, anticipated what the telescope would witness, a cosmic event so gargantuan it would send shockwaves not just through Neptune's atmosphere, but through our very understanding of the outer solar system. During one of these scheduled deep sky observation cycles, with the JWST precisely targeting Neptune's vast southern hemisphere, something anomalous, something utterly unexpected, materialized in the telescope's hypersensitive infrared detectors. There was a sudden and massive burst of infrared radiation, a sharp, blinding spike that was entirely out of character for the typically cold, uniform infrared signature of the ice giant. Neptune, known for its consistent chill, had suddenly flared with an intensity that screamed external energy. This bewildering spike was almost immediately followed by an unmistakable visual disruption on Neptune's outermost cloud layer, a colossal disturbance too immense, too chaotic, to be dismissed as mere weather phenomena. The implications were immediate and staggering. It wasn't an internal storm. It was a wound, a cosmic bruise on the face of a giant. The data streaming back to Earth from the JWST began to paint a terrifyingly clear picture. A deeper analysis of the infrared data meticulously revealed thermal gradients that spoke volumes. An external source of energy had been violently introduced into Neptune's atmosphere at incredibly high velocity. This wasn't a storm brewing from within the planet's frigid depths, nor was it a result of its internal thermal convection processes, which are typically slow and predictable. Instead, every piece of evidence, every captured photon, every spectral signature, pointed unmistakably to one terrifying conclusion: an external impact. Something immense, something traveling at unimaginable speeds, had violently collided with Neptune, delivering a colossal amount of kinetic energy into its methane-rich atmosphere. The tranquility of the outer solar system had been shattered by a single devastating blow, a cosmic punch that resonated across billions of miles. The entity that dared to strike the distant giant was, as suggested by meticulous follow-up spectral analysis and advanced computational modeling, a colossal cosmic projectile. Its size was estimated to be anywhere between 30 to 50 kilometers in diameter, an object truly formidable, about the size of a large asteroid or a small trans-Neptunian object, like a dwarf planet. Unlike the rocky surfaces of Earth or Mars, Neptune's incredibly thick atmosphere, composed predominantly of hydrogen, helium, and methane, doesn't allow for clear surface imaging. Therefore, observing a traditional crater or a lasting land scar from this impact was impossible. Yet, the immediate aftermath left an unmistakable signature. The immense energy released by the collision created colossal shock waves in the planet's high-altitude cloud bands, spiraling outward from the impact site like ripples from a stone dropped into a cosmic pond. These shock waves were so powerful they propagated across Neptune's southern hemisphere, visibly displacing massive high-altitude clouds and temporarily distorting the planet's faint, icy ring system, an unprecedented disruption visible even to Earth-based observers through the aid of JWST's incredible clarity. JWST's continuous observations documented a significant change in the albedo, or reflective brightness, of the surrounding atmosphere near the impact zone. What had previously been a relatively stable, cool, and uniformly dark zone on Neptune suddenly transformed into one of the brightest thermal hotspots the ice giant had exhibited in decades of observations. This was direct evidence of the immense heat generated by the impact, radiating outwards into the frigid depths of space. The JWST's advanced sensors were not only able to capture the immediate infrared flare of the collision but also meticulously traced a trail of particulate debris that lingered persistently around the impact site. This haze was likely consisting of remnants from the colliding body itself, pulverized fragments of its icy and rocky composition, now suspended in Neptune's upper atmosphere, a cosmic forensic trail revealing the nature of the assailant. This ethereal trail of cosmic dust remained suspended in Neptune's upper atmosphere for several Earth days, forming a faint hazy arc that was strikingly visible in both the infrared and even certain narrow visible spectrums. Scientists painstakingly inferred that the impactor was composed predominantly of volatile ices and rock, a composition remarkably similar to many Kuiper Belt objects, KBOs, that gracefully orbit just beyond Neptune's distant path. This crucial compositional hint suggested a tantalizing possibility. The object could have been a rogue KBO that had strayed violently from its accustomed orbit, perhaps subtly influenced by gravitational perturbations from the other ice giants, Uranus or even Neptune itself, before being drawn in fatally by the very planet it had once orbited at a respectful distance. It was a rogue bullet from the solar system's distant, icy frontier, an unpredictable harbinger of the chaos that still lurks in the outer darkness. One of the most fascinating and alarming aspects of this sudden collision was the planetary response it elicited from Neptune itself. Neptune's magnetic field, already a peculiar enigma due to its extreme tilt relative to its rotational axis and its highly variable nature, showed immediate and profound signs of short-term disturbance. The charged particle environment in the direct vicinity of the planet changed significantly, as indicated by an unusual flux in energetic particle readings. This wasn't just an atmospheric event, it was a shock that resonated through the planet's very core. This implies that the impact was not merely a surface or atmospheric phenomenon, but one with far-reaching ramifications on a planetary scale. If the impactor penetrated deeply enough, it could have temporarily disrupted the complex convective motions within the planet's interior layers, potentially influencing the very generation zones of its peculiar magnetic field, a ripple effect reaching into the heart of the ice giant. Beyond the sheer physical drama of the event, the detection of this massive impact has forced astronomers and planetary scientists across the globe to profoundly reassess the dynamic activity of the outer solar system. For decades, it had been a widely held assumption that such massive collisions were far more common during the solar system's tumultuous formative years, billions of years ago, when debris was more densely packed and orbital paths were far less stable and predictable. The thinking was that the solar system had largely cleaned itself up over eons, with major impacts becoming exceedingly rare events. However, this collision, captured with unprecedented clarity, irrevocably shattered that assumption. It starkly revealed that even in the supposed quietude of the outer solar system, remnants of its chaotic youth still lurk, capable of delivering devastating blows that could fundamentally reshape planetary surfaces or, in Neptune's case, its atmosphere, proving that the universe is far from a static, predictable place. The immediate aftermath of the colossal impact on Neptune was a profound shock to the scientific community. While initial models had predicted the general mechanics of such an event, the sheer scale of the observed atmospheric disturbance and the lingering debris trail demanded a rigorous re-evaluation of established planetary impact theories. Scientists from institutions worldwide swiftly collaborated, pooling data from other observatories, both ground-based and space-based, to corroborate JWST's findings and gather additional spectral information. This wasn't merely an academic exercise, it was an urgent necessity to understand a phenomenon that, until now, had been considered statistically improbable in the modern solar system. The incident served as a chilling reminder that even in the vast, seemingly serene emptiness of space, unpredictable and catastrophic events can still unfold, catching humanity entirely off guard. The composition of the impactor, inferred to be a mix of volatile ices and rock, provided crucial clues about its likely origin. This signature strongly pointed towards the Kuiper Belt, a vast, icy reservoir of primordial material stretching beyond Neptune's orbit. The Kuiper Belt is home to countless dwarf planets, comets, and smaller icy bodies, remnants from the solar system's formation. While most of these objects maintain stable orbits, gravitational interactions, particularly with the giant planets, can occasionally perturb their paths, sending them hurtling inwards towards the inner solar system. The Neptune impact was a stark demonstration that these perturbations aren't just theoretical. They are powerful, tangible forces that can unleash cosmic projectiles of immense destructive potential, proving that the outer reaches of our solar system are far from dormant. What made this event even more unsettling was its potential implications for the entire outer solar system's stability. If an object of this size, originating from the Kuiper belt, could suddenly deviate and strike a major planet like Neptune, what does that imply for the long-term orbital stability of other Kuiper belt objects, and even for planets closer to the Sun? Could there be a cascade effect? Scientists began to model complex gravitational dynamics, attempting to trace the impactor's potential journey and identify any subtle influences that might have nudged it towards its fatal encounter. The very act of observing this collision, previously a hypothetical scenario, opened a Pandora's box of questions about the hidden dangers that might still lurk in the far reaches of our cosmic neighborhood, making the tranquil blue giant a stark, distant warning. The precise trajectory and velocity of the impactor were meticulously reconstructed through a process akin to cosmic forensics. By analyzing the angle of the shock waves propagating through Neptune's atmosphere and the initial infrared flare, scientists could infer the impactor's approach vector. The sheer speed at which it struck suggested it had likely undergone significant gravitational acceleration as it fell towards Neptune, a final, fatal embrace with the giant it was destined to collide with. This hypervelocity impact meant that the kinetic energy delivered was truly immense, far more than simply the object's mass would suggest. It wasn't a gentle bump. It was a cosmic hammer blow, instantaneously releasing more energy than thousands of nuclear weapons, sending titanic ripples of force through the planet's upper atmospheric layers, a momentary scar etched into the very fabric of the gas giant's swirling visage. Beyond the immediate physical effects, the incident prompted a widespread reassessment of planetary defense strategies, particularly concerning threats originating from the outer solar system. While asteroid detection programs primarily focus on near-Earth objects, NEOs, the Neptune event underscored the vulnerability of our solar system to larger, more distant and harder-to-detect bodies. An object of 30 to 50 kilometers in diameter, if it were on a collision course with Earth, would represent an extinction-level event, far surpassing the Chicxulub impact that wiped out the dinosaurs. The fact that such an object could seemingly come out of nowhere from the distant Kuiper belt highlighted a significant blind spot in humanity's cosmic vigilance, a chilling realization that true safety requires eyes on every corner of our vast celestial home, including the most remote and seemingly quiet regions. The unexpected response of Neptune's magnetic field was another perplexing puzzle that demanded immediate attention. The ice giant's magnetosphere is already unique, characterized by its non-dipolar and highly variable nature, unlike Earth's relatively stable magnetic shield. The sudden flux in energetic particle readings and the short-term disturbances implied that the impact's energy might have momentarily penetrated much deeper than just the atmosphere, potentially affecting the planet's internal dynamo. This suggests that the impact could have temporarily disrupted the intricate convective motions within Neptune's superpressurized water, ammonia and methane ice layers, where its magnetic field is thought to be generated. The implications are profound. A single external event could even temporarily alter the very fundamental forces that govern a planet's protective shield, leaving it vulnerable to the harsh radiation environment of space. This magnetic anomaly fueled intense scientific debate. Was this a mere transient effect, or could such an impact have longer-lasting consequences for Neptune's unique magnetic architecture? Further studies were immediately commissioned, utilizing every available instrument to monitor Neptune's ongoing magnetic behavior. The event highlighted a critical gap in our understanding of how giant planets, with their deep, complex interiors, respond to such external shocks. It was a stark reminder that even our most comprehensive models of planetary physics might be incomplete, and that real-world events, however rare, can reveal entirely new layers of complexity, forcing scientists to rethink fundamental principles. The blue giant, far from being a simple, static orb, revealed itself as a dynamically responsive entity, capable of reacting to cosmic blows in ways we never anticipated. The Neptune impact also provided an unprecedented opportunity to study atmospheric dynamics on a planetary scale in real time after a massive energy injection. The spiraling shock waves, the displaced cloud bands, and the lingering debris offered a unique laboratory for atmospheric scientists. They could analyze how such immense energy dissipates through a thick, methane-rich atmosphere, how turbulence is generated and propagates, and how it influences global weather patterns. The observed changes in albedo and the formation of thermal hotspots provided empirical data invaluable for refining climate models of giant planets, not just Neptune. It was a tragic but invaluable accident, a cosmic experiment forced upon us, revealing secrets about atmospheric responses that would otherwise take centuries of observation to deduce, fundamentally altering our understanding of planetary meteorology far beyond our own Earth. Moreover, the event sparked renewed discussions about the frequency of such collisions in the outer solar system. If a 30 to 50 kilometers object struck Neptune now, billions of years after the solar system's formation, does this imply that larger, potentially hazardous objects are still lurking in the Kuiper belt in greater numbers than previously estimated? Or was this a truly rare one-in-a-trillion event? The debate is intense, with some scientists advocating for increased surveillance of the outer solar system, while others maintain that the current models of orbital stability are largely accurate and that such events remain exceptionally uncommon. Regardless of the statistical likelihood, this collision served as a chilling, undeniable proof that the cosmos remains a place of dynamic forces and unpredictable dangers, even in its most remote and seemingly tranquil corners, a silent threat still very much in play. This dramatic cosmic incident on Neptune didn't just capture images, it captured the imagination, reminding humanity of the raw, untamed power of the universe. It reinforced the notion that despite all our technological advancements, despite our ability to peer across billions of miles, there are still profound mysteries and potential dangers lurking in the vast darkness beyond our immediate reach. The tranquil blue giant, once a symbol of serene cosmic distance, has now become a stark and potent reminder that the solar system, even in its advanced age, is far from a stable, predictable clockwork, constantly evolving, constantly surprising, and endlessly capable of revealing its hidden, devastating secrets.